Okay, a few more example problems from trigonometric functions. And so we're going to look at first finding the arc length. We want to find the length of an arc subtended on a circle. So that means the circle is cutting off the angle, and the angle that you see is here. So in yellow, there's a little highlighted there. So we want to know what the length of the arc is. The arc is the S, and the S in this case is going to go all the way from one end of the angle to the other. So it's going to be that orange highlighted area. So, and the circle has a radius of 3. So when we do these, we're going to remember that our angles must be in radians because theta is equal to S over R, as you see. So we just want to know what's the length of the arc length. So we're going to plug in here. My radius is 3, and my angle is given in radians, so that's a good thing. 2 pi over 3. And if you're not sure, see, I already have it drawn here. If you're not sure for drawing purposes, you might want to look at this as 120 degrees to figure out where you need to place it between 90 and 180. But in this case, you get an arc length that's approximately equal to 6.28 units, right? 6.28. So 2 pi. Now, what you might do when you're handling these is you might have an angle given in degrees, and you might say, oh, S is equal to 3 times 120, which would turn out to be 360. And you're thinking, oh, wait a minute, the arc length can't be that big. So with your reasoning, you would say it can't be 360 because you have a radius that's only 3. That situation just wouldn't work. You can't go 360 units through an arc length when you only pass through 120 degrees, even if you do a quick estimate with a triangle. So that used to work for me. So keep in mind, the S is the arc length in that formula, and the theta is an angle in radians. Remember that if R is equal to 1, then S is equal to theta. So, okay, so I'll give you that one. The arc length was 6.28. In the next example, we want to confirm that cosine is an even function and sine is an odd function. So what we're going to do is we're going to use the ratios that I gave you previously where cosine of the angle theta is x over r. Well, if you look at the situation here where the positive angles go counterclockwise, right? So up here you have a CCW, right? And down here you have a clockwise angle. But say that they're the same except going in opposite directions. So cosine of theta is going to be the ratio of the x over the r. And you're pulling those from x over r. And then when you look at the cosine of negative theta, it's still x over r, but it's a different situation. It's the one down here in the fourth quadrant, okay? So in this case, we can just say, therefore, cosine theta is equal to cosine negative theta. Okay, so done, QED. The next one is sine theta. So if you have sine theta is equal to y over r, what you want to say for an odd function, oh, by the way, I put those up here and forgot about it. So for an even function, it has y-axis symmetry. Normally when we think about even or odd, you have f of negative x is equal to f of x, or I said that backwards, f of x is equal to f of negative x. So that's why I chose to say cosine theta is equal to x over r, and then cosine negative theta is the same thing. And so it gives me the relationship I need for an even function. If it's an odd function, then we have the relationship here that negative f of x is equal to f of negative x. So that odd functions have origin symmetry. So we just want to prove that with sine. So in this case, I want negative sine theta. So in that case, negative sine theta would be the negative of y over r. And then sine of negative theta is going to be negative y over r. So you can see that you can manipulate this and bring the negative sign out front if you want to, but we would simply then say that negative sine theta is equal to sine negative theta. It has that relationship that we expect from all odd functions. So we could say, therefore, where the cosine function was even, the sine function is odd. And when you look at the graphs, when you look at the graphs, you can see that y-axis symmetry, right? You can see how the left-hand side is the same as the right-hand side. And you can see the origin symmetry with the sine function, where you have the function is even going through the origin, but where with the y-axis symmetry, you have a point like this, pi over 2, 0. That means you have negative pi over 2, 0. I could choose other points. I guess it would be a little bit better, but that'll be fine for right now. And then the origin symmetry, of course, if you pick this point where you have pi over 2, 1, pi over 2, 1, then you have this point down here, negative pi over 2, this one, negative 1. Okay, and the x's and y's just change signs. Okay, so that's what we've confirmed, that that cosine is an even function, sine is an odd function. Okay, so then we have finding, and if this is going a little too fast and you need to slow it down, pause your video, maybe even slow it down, or speed it up, whichever fits your needs. But if you need to slow it down or review it, then that's something that you have to your advantage. So this next problem, example 3, we want to find trigonometric values. Find all of the trigonometric values of theta if sine theta is equal to negative 3/5 and tangent theta is less than 0. So this is actually an and statement. And so I'm going to come down here first. I have this already written. I want to know where tangent theta is less than 0 and sine theta is less than 0. And that occurs in quadrant 4. So the first step I'm going to take is I'm going to go up there and I'm going to say sine theta is negative 3/5. So I can let that equal a y over r ratio. And I'm going to let y equal negative 3 and r equal 5 in that ratio. It seems random, but not really, because it's just in simplest form. I could make y negative 6, and then r would be 10. It's just multiplying by a factor of 2, but I use what I have here. It's a little easier. So now, for what I do is I have the sine function, so I'm going to jump right over to the cosecant function. I'm just going to say that that's going to be negative 5/3. Just give the reciprocal of that, because remember that cosecant is then the r over y, so all I have to do is flip them. For the cosine, where the cosine is now x over r, and then the secant is r over x. So for the cosine, notice I don't have an x there, so I had to come up here, and after some consideration, I'm missing the x value, so I have to get the x in there. So I use the Pythagorean theorem with that, plug things in, and I get x is equal to plus or minus 4. But since the point must lie in the fourth quadrant, x has to be positive. So we're going to get x is equal to 4 here. So now I'm ready to plug that in for my ratios. So cosine is 4 over the r value, which is 5. Then for the secant, I'm going to do the reciprocal, 5 over 4. And that's done. Now that we have all three of our sides of the triangle, and here's my theta. I actually should put that in there here, theta. And notice I'm writing this just as theta as a clockwise angle. It doesn't matter if it's clockwise or counterclockwise of this. It could be either, but in this case, I'm just going to make it the one that's within the triangle. So now the tangent, remember that is the y over x, and then of course the cotangent is the x over y. So then the ratio is then negative 3 over 4 for the tangent, opposite from the angle over adjacent. So, and then cotangent, then of course is the reciprocal, negative 4/3. Okay, so that finishes example 3. I'm going to move on to the next one, which is a graphing one. I'll probably stop there and then pick up to do the remaining problems on the second video. So if you look at this, we're graphing a trigonometric function. The form for the trigonometric function graphing would be y is equal to a cosine b times the quantity x minus c plus 1. Remember, the c is going to give you, that was going to be a d here, plus d. The plus 1 is in the problem, but the c does that left and right shifting, and the d does the up and down shifting, and the a and the b control the shape of the graph. So the first thing I'm asked for is the period. So you're just going to put notice that I take the equation, factored out the 2, and remember it's kind of weird factoring again where you're dividing each term by 2. So then you can see that the C value that I spoke about with the translations is going to be pi over 2. So I get this function. I'm going to highlight this in orange right here. So this is my function that I'll be graphing. Okay, but we're going to do this as a process of translations using the information. So first we get the period. So the period is pi. So we have the period is pi. We have the domain is from negative infinity to infinity. So I can input anything, and you know what the trig functions look like for the sine and the cosine already. So, and the range goes from -2 to 4. Now the range is kind of tied with the fact that the amplitude is 3. So that means that if you're shifting your graph pi over to the right and 1 up. Notice what I did. I drew that line right away, y is equal to 1, to kind of connect that. That's going to be my line of equilibrium in the end. But here's how I start. With number 1, first thing I do is I graph the pink graph as the shape of my final graph. And all I have to do once I get that, including the 2 things, the amplitude and the b for the period. So where my period is pi, I can get a start point and then do my quarter cycle movement with the amplitude of 3. So that's what I'm going to need to use. And then in my next step, I'm going to shift it to get the purple graph and then get the green graph. And that will be part of my finalized graph. Okay, so let's take a look at this. So starting 3 cosine 2x, I use this fact that 3 times cosine of 2 times 0 is equal to 3. That gives me a start point. So let me go back to my pink pen, make this a little bit bigger. So I start here at that point. And then that means after pi units, I go through a complete cycle. So I end up there. And that's at pi, and the point is pi 3. I'm not going to label everything. You can see the scale. So then in between that, I'm going to move my quarter cycles, recognizing that I'm going to go down in quarter cycles. So when I'm at pi over 4, I've gone a quarter cycle. I go to my equilibrium. Remember, this is the pink graph. It's not my final graph. Then I go down 3 units. That's the amplitude. And then I go back up to the equilibrium. And then that's where I ended at pi 3. Okay, so that gives me one cycle, one complete cycle of the graph of 3 cosine 2x, which gives me the shape of the graph. Now, in my next step, I'm going to shift that graph pi units to the right, because when we subtract from the x, that's the movement we're moving. We're moving c units, and in this case, pi over 2 units to the right. So you see the purple graph, I'm not calculating any inputs and outputs. All I'm doing is I'm just giving the shape of the graph as I'm translating, and I'm just going to draw a real quick arrow, then erase it. Pi over 2 units to the right, point for point. But the easiest points to use are those that fall on those quarter cycles. Okay, so there's the purple graph, pi over to the right. I move every point 2 units to the right. I kind of look, a good suggestion that was made to me when I was a calc student is use the tick marks that you have or you build. And sometimes it's easier to draw your own graph than to use a graph provided. I'm going to go pi over 2 units to the right, so that turns out to be 2 tick marks noted from the pi over 2 on the x-axis. Now the last step is I'm going to go 1 unit up, so the units along the y-axis are 1 unit apiece, so I'm going to go 1 tick mark up, okay? So shifting my green graph, okay? Now I could duplicate this. I guess it would probably be a little easier to duplicate it than it would be to redraw the whole thing, but let me see now if I messed up here. Let me undo it and duplicate it and move the graph. No, I'm only getting one part of it, so I'm not going to do that. Move that down here. So all you have to do at that point, let's make the graph a little bit thicker than what I have and stay green. Okay, so I've got this point, this point, this point, this point, and this point, and now I'm going to continue that process using my line of equilibrium. I'm going to start, remember, I'm 3 units up from the line of equilibrium. I'm going over 2 tick marks and down 3 here. Okay, so if I continue this, I'm going to just darken this a little bit for my final graph. So I'm going to go over, and you can see that I'm going to go over 1 tick mark and down 1. Okay, so building that. So I'm going to go over 1 and down 3, over 1 to the left and up 3. So now you have this U shape here. It's kind of off a little bit, but not too bad. Okay, over 1 and up 3, over 1 and over to the left and down 1. So now I have this one. Okay, and I have to go back and fix this one. When it gets a little bit sloppy, I don't like that. It gets a little bit better, I guess. Okay, and then completing this further, going to the left 1 and down 3, to the left 1 and up 3. So just completing the graph, not calculating anything. All we're doing is, here I'm going to put just an arrow there, is duplicating that cycle that we drew first, the green cycle that we drew first. Okay, and there we go, there we have it, and I need that meter. And continuing out there. So we have now drawn the graph of this y is equal to 3 cosine, oh, there we go, 2 times the quantity x minus pi over 2 plus 1. Now what I've done is I've put a table down here. Sometimes as a student I like to check out the table and make sure that I had the values correct. So I would choose values that are what I call compatible. So I would pick values like 0 or pi over 2 just to see what I would get. And as it turns out, when you input pi over 4, if you input pi over 4, you get 0 for an answer. So this is the pink graph. So this is where I started before I did a shifting pi over 2 to the right and 1 up. So that finishes up our graph of y is equal to 3 cosine 2x minus pi, and then plus 1, considering all the translations that we have. Okay, when you come back, we're going to pick up with finding the frequency of a musical note. Frequency then is, if you can see down here, frequency is the reciprocal of the period, and we very often use it with sound in units of hertz. But I'll be back in the next video for that. Okay, see you when I see ya. This is Mrs. Allen out.